Thank you for joining me today in this presentation, and thanks to GTT for giving us the opportunity to share our work with you. I'll share the work that XPS has done to develop a ChemApp interface for real-time digital twin modeling of metallurgical plants. My co-authors are Arina Moraes and Nicolas Lazar from XPS Process Control Group. My name is Tanai Marin. I am Superintendent of Process Simulation and Modeling at XPS. Before getting started, I'd like to give you a brief introduction to XPS. XPS Expert Process Solutions is located in Falconbridge, Ontario. It has more than 60 years of corporate memory. Started out as a former Falconbridge Technology Center, FTC, providing corporate research with a mandate to develop new process technology and support Falconbridge operations. Since 2007, after Xstrata takeover, XPS became a fully autonomous consulting and test work service company. This structure has been maintained after Glencore's takeover from Xstrata. Over the last 14 years, XPS has been providing technology solutions and test services in ore body characterization, flowsheet development, operational support, and asset integrity management for most commodities including nickel, sulfide, and laterite, copper, lead, zinc, gold and PGEs, rare earth, chromite, lithium, potash, and industrial minerals. Currently, XPS consists of 7 main technical groups: mineral science, mineral processing, pyrometallurgy, hydrometallurgy, process simulation and modeling, process control, and materials technology. Here is the outline for today's presentation. I'll start by providing a description of the main objectives and motivation to develop this interface, a description of the interface itself, how it is implemented in the plant control system, and I'll finalize with a brief description of an example of its implementation where we developed a real-time model for a finishing converter. The main purpose of the interface is to be able to create or develop dynamic models of metallurgical reactors. The idea is that these models can then be fully embedded or integrated into an industrial plant control system, receiving real inputs from plant measurements and events and communicating the results of the model back to the control or data system. The interface builds each model as a computational object, as in object-oriented programming, which allows to create several instances of similar unit operations or interconnect different models of an existing plant. At the end, the metallurgical reactor model acts as a digital twin of an existing equipment or unit operation. It can provide real-time estimation of the reactor's stream compositions and amounts, impurity deportment, product quality, etc. This type of model can then be used to improve process performance, minimize losses, minimize environmental emissions, achieve better operational conditions, leading to extended service life, etc. XPS interface is basically a dynamic link library with the main purpose to simulate metallurgical processes as computational objects. At the high level, it requires 3 main components. First, an input data set describing the system to solve, elements, compounds, mixtures, etc. A solver, in this case ChemApp, which is used to calculate the thermodynamic equilibrium based on the given input conditions and amounts. And finally, a host software providing input-output communication to the user of plant information. In this case, Emerson's Plant Web Optics Analytic. More details on this later. When using ChemApp, the input data files are compatible with ChemSage formats. Of course, proper licenses for thermodynamic input files prepared by GTT or by the use of FactSage software must be ensured on a case-by-case basis. In our case, XPS have developed a large private thermodynamic database of solutions and compounds covering from non-ferrous, ferrous, precious, and light metals to oxides, sulfides, etc. The origin of the interface comes from M4D GCI, General ChemApp Interface, to provide support to link ChemApp routines into other platforms. Originally, this was used to create the ChemApp interface for COMSOL or Arena software. Now compatible with Emerson's Plant Web Optics Analytics, it requires a compatible thermodynamic input file, which can be a license format, .cst, or open text format, .dat. Currently, the library has incorporated additional functionalities to the interface that expand the original capabilities. These include GTT's ChemApp library, of course. This is the main component currently for the library to create thermodynamic-based models, but also the XPS general mass balance. And this allows to simulate simpler unit operations, for example, when a full-blown thermodynamic model is not required. Also, we're working to add in the future other solvers developed by XPS, currently in development, such as artificial intelligence or machine learning, or to add ODE or ordinary differential equations for transient kinetic modeling, as well as other third-party solvers. As mentioned before, the library is built as a 64-bit DLL compatible with C# and other programming languages, providing high-level object-oriented structure of classes and methods for process simulation and metallurgical reactors. Here is a graphical representation of the structure of the interface, showing the three main components necessary. The input data describing the system to model, that is, the system's component, phases, phase constituents, stoichiometric matrix, thermodynamic parameters, etc. Then at the center is the solver, which is GTT-ChemApp for thermodynamic-based models. And here, the interface can perform all of the ChemApp routines, including normal equilibrium calculation, specifying input amounts, temperature and pressure, or enthalpy-based calculations, phase targets, and also constraint-free energy calculations for coupled equilibrium and kinetically constrained systems. The user interface, in this case, is provided by Plant Web Optics Analytics software by Emerson. This is the host software where the reactor models are created and provides the link between the plant measurements and events and the interface, triggering the setup or calculation routines for the model. The Plant Web Optics Analytics is a process data analysis software that empowers plants to reach operational excellence by detecting abnormal events, delivering knowledge to operations, managing performance deviations, and increasing visibility across the enterprise. The Project Studio IDE consists of a graphical development environment where application developers can configure applications to proactively monitor the enterprise performance and process conditions, perform root cause analysis, execute and supervise business workflow, and state transitions diagram. Plant Web Optics Analytics integrates multiple applications and systems using industry standards such as OPC, ADO.NET, SOA, and WCF, while custom applications can be added as data source using Plant Web Optics Analytics plugin. Here, 4 different modules available in the Project Studio IDE are shown: the rules, RCA, workflow, and map. The main goals of the rules modules are early detection of abnormal conditions, transform raw data into information and knowledge, implement what-if and simulation scenarios, easily and rapidly develop real-time operations logic. The root cause analysis module allows to capture operational knowledge, identify root cause of operational issues, reduce the time of resolution cycles, empower operators with knowledge at their fingertips. The workflow module is the main module where the reactor model is developed. It allows to graphically design static and generic workflows using sequential and parallel activities. These activities can interact with more than one application, synchronizing data, execution, or interaction flow between them. Workflows can be triggered automatically by events detected by the rules and/or RCA modules, or manually by the end users. In general, this module allows to schedule and automate work activities, enforce best practice, synchronize application through events and activities, reduce resolution time, and prevent decision bottlenecks. Here is a representation of the model logic implemented in the workflow module to simulate a digital twin model of the Sudbury iron ore smelter's finishing converter to provide real-time iron endpoint control during the cycle. There are 2 finishing converters at the smelter, receiving matte input from the electric furnace and from 2 hybrid converters. The model automatically detects the start of a blow through appropriate event frames and initializes the model. Identify sources, amount, and composition of feeds, including custom feeds, flags, slack transfer, etc. The workflow consists of 2 main branches. At the left-hand side, we can see the initialization routines as well as the target calculations to estimate the blow duration and flux addition. After the first branch is completed, the model enters into an iterative loop following the progress of the converter blow. During the iterative process, the workflow can update input information even after the blow has started. For example, in the case of receiving late information of a feed assay, triggering an automatic correction and recalculation of the model to incorporate the new data. In addition to this, the model can correct itself in between blows if a check sample is available, which helps minimizing and absorbing some of the uncertainty associated to the input measurements and assays. For the converter digital twin model, PlantWeb Optics Analytics communicates with the Pi Data Archive, Pi Asset Framework, Pi Event Frames, LIMS, DCS, and CQL databases. The Pi AF attributes and Pi Event Frames provide the triggers and inputs to be used on the model calculation. The thermodynamic model for each converter is created as an instance of the object-oriented version of the XPS process simulation interface. At each iteration, PlantWeb Optics Analytics writes the estimated converter iron composition in math, the blow time remaining, slag quality, and other model outputs to the DCS for a full integration to the control system of the plant. Finally, to summarize, XPS has developed a process simulation interface that allows real-time modeling of high-temperature reactors fully integrated with plant control systems. The interface uses GTT's ChemApp library to simulate reactors involving complex multi-component and multi-phase thermodynamic systems. The interface is integrated to Emerson's PlantWeb Optics Analytics software to trigger model events, communicate with existing control and information systems such as Pi Data Archive, Pi Asset Framework, Pi Event Frames, LIMS, DCS, and CQL databases. XPS has successfully developed and implemented this approach to simulate finishing converters at Glencore Sudbury Integrated Nickel Operations Smelter, demonstrating the robustness and flexibility of the model as well as operational improvements. Thank you very much for your attention. I hope this has been interesting for you, and I'd be happy to answer any questions or discuss any comments that you may have.